Welcome to Precalculus Algebra, the video on symmetry part 1. And all we mean by symmetry is, or rather we say a graph is symmetric or has symmetry when the graph is unchanged after some reflection, and that could be in the x or the y-axis, or some rotation. So the types of symmetry we're going to talk about are symmetric with respect to the y-axis, symmetric with respect to the x-axis, and when a graph is symmetric with respect to the origin, and we also say that it's symmetric with respect to 180-degree rotation. Okay, let's start off with symmetry with respect to the y-axis and see what we're talking about. Alright, so all we mean by that is symmetric with respect to a y-axis is when a graph has a mirror reflection across the y-axis. And by looking at this graph, we see that if the point xy is on the graph, then clearly we want this point over here on the graph as well. Well, what is that point? That point's the reflection of this point. And what do these 2 points have in common? Well, here you go x units to the right, and here you go x units to the left. Now, here, if x is positive over here, we have negative x over there because we're going to the left. And likewise, they're both up how far? Well, they're both up the unit or the value y. So if the point xy is on the curve, so is the point negative xy. Okay? So that's going to be our test for seeing whether or not a graph is symmetric with respect to the y-axis. We want both the point xy and the point negative xy to be on the curve. So for example, let's say you have the curve y equals x squared. Okay, so on this curve is the point xy. Now we're also hoping that the point negative xy is on this curve as well. So what we're going to do is we're going to replace x with negative x and replace y with y, or just keep y the same. And when we do that, let's see, the y remains the same, so y is still y, but then the x becomes negative x. So we have this. Okay, so this is what we've basically done is taken this point, or these coordinates, negative xy, and plug them into that. And what do we get? Well, y equals negative x squared, which is the same as y equals, well, when you square negative x, it's going to be, let's erase that parenthesis. Negative x squared is just y equals x squared. Okay, and this is the curve satisfied by the point negative xy. Now what we see is that xy satisfied this, and negative xy satisfies that, right? But the equation that negative xy satisfies, y equals x squared, is the same as the equation that is the same as what xy satisfies, right? So xy satisfies this, negative xy satisfies the same equation. So both xy and negative xy are on the same curve, right? So the fact that these equations are the same means that both xy and negative xy are on the same curve. And that means that's enough to tell you, so therefore the curve y equals x squared is symmetric about the y-axis. Okay, in other words, if you were to graph this this curve right here, you're going to find that it has it looks like the graph is has a reflection across the y-axis, and we know this is true, right? Because the graph of y equals x squared is a parabola that looks something like this. Okay, it has a right branch and a left branch, and there's mirror symmetry across the y-axis. Another example of a curve that has that would be y equals the absolute value of x. And we can test that as well. So let's say that this curve is satisfied by xy, and the question is, what happens when you replace x with negative x and keep y the same? Well, the equation is going to become y equals the absolute value of negative x, right? That's satisfied by negative xy. But this is the same thing as y equals the absolute value of x. So negative xy satisfies this equation, which is the same equation satisfied by xy. Because both of these points are on the same, or satisfy the same equation, they're on the same curve, and therefore, by our criteria, this curve must have y-axis symmetry as well. Okay, what about when a curve is symmetric with respect to the x-axis? Let's see an example of that. So with respect to the x-axis, all we mean by that is that the curve has been reflected across the x-axis. And we can see that if this is the point xy, okay, well, what must the coordinates of this point be? Well, that is the mirror image of this point. Well, what stayed the same? Clearly, the x-coordinate has stayed the same, but instead of positive y, it's going to be negative y. So what we're going to do to test for x-axis symmetry is we're going to keep the x the same, and we're going to replace y with negative y. And we're hoping that this point satisfies the same equation this point satisfied. So for example, let's say you had the equation x equals y squared. Okay, and that's satisfied by xy. Let's go ahead and do what we said we're going to do. We're going to keep x the same and replace y with negative y. So it's going to become x equals negative y squared, and that's satisfied by x negative y. And so this is x equals, but then when you square negative y, you get y squared, and that's satisfied by x negative y. So x negative y satisfies this, but that's also the same equation satisfied by just when it's x positive y. And because both xy and x negative y satisfy the same equation, that tells us that the graph of this is symmetric with respect to the x-axis. And if you graph this curve right here, the graph is a parabola on its side, so it looks something like this. It's got a branch here and another branch like that. And it has clearly symmetry, reflection symmetry across the x-axis. Okay, an example of a curve that doesn't have this symmetry would be something like this. X equals y squared plus y. So if you try to test this curve for this type of symmetry, you say, okay, we start off with xy, and according to this test, what you do is you keep x the same and you replace y with negative y. So x stays the same, and you get, let's see, negative y squared plus negative y, right? Y's been replaced with negative y. And this is x equals y squared, but then minus y. And this is the equation satisfied by x comma negative y. So let me ask you, xy satisfies this equation, but x negative y satisfies this equation. And these two equations are different. And that means this curve will not contain both xy and x negative y. So it doesn't have symmetry with respect to the x-axis. The graph of this curve does not look, when you graph it, it's not going to be a reflection across the x-axis. It failed this test, if you will. Okay, finally, there's one more type of symmetry. Let's see what that is. That's symmetry with respect to the origin. And for this type of symmetry, what you do is you look at one branch and you imagine rotating it about the point, the origin. And upon rotation, 180 degrees, if the curve ends up on top of the other side, the other branch, then it has that symmetry. In other words, if I rotate this 180 degrees, it lands right on this branch. And if I rotate this 180 degrees, it lands on that branch. So if a curve has this symmetry, we say it's symmetric with respect to the origin. Now, what has to happen as far as x and y are concerned? Well, let's say you had a point here, call it xy. Well, that point, clearly we want, upon rotation, we want that point to fall onto this point right here. So, well, what happens? If you go to the right x and up y, well, likewise, you want to go to the left x, right? And then down y. So this point's going to be not positive x, but negative x. And then not positive y, but negative y. And so you can see what our test is going to be, right? You replace x with negative x, and you replace y with negative y. And if you get the same equation, that means this point satisfies the same equation as that point. So for example, take the equation, let's see, how about y equals x cubed. So let's say xy satisfies that, according to just how it's written. Now if I replace, what I'm going to do is I'm going to replace x with negative x, this is my test, right, for symmetry about the origin, and I'm going to replace y with negative y, and I'm hoping the curve I get when I do this replacement, I'm hoping the curve ends up being the same thing. Let's see. It's going to be negative y equals, and then x with negative x, it's going to be negative x cubed. And we have negative y equals, and then when you cube negative x, it remains negative x cubed. And now you can divide both sides by negative 1, and you get y equals x cubed, right? So this is satisfied by negative x, negative y. And what we see is this curve, right, y equals x cubed, is the same as the curve satisfied by xy. What does that mean? It means that this curve contains not only xy, but it contains, for every xy, it contains negative x, negative y. And that's going to lead to this type of symmetry, right? Every time you have xy, you're also going to have negative x, negative y, right? Here's some xy, different xy. Well, you go to the right x and then up y. Likewise, you go to the left x and down y. So it's going to contain that point as well. And we call that symmetry with respect to the origin. So, and as far as 180 degree rotation, notice that you can always draw a line through the origin to the point of the other point of symmetry. Likewise, right here, a line through the origin. And that line through the origin indicates that you can rotate 180 degrees. You can rotate that point 180 degrees to get to the other corresponding point, right? Like this point right here, I can rotate 180 degrees and remain at the same distance from the origin to get the other point. Okay, so we're going to see these types of symmetries as we progress in the course, and we're going to have names for, we're going to name these symmetries differently when we have functions, which is why this video is Symmetry Part 1. Okay, until next time.